Theovis, the idea made visual. Last time we met, the function that survives differentiation. Now we let several quantities change at once, each tugging on the others, and watch a tangled mess become beautifully simple.
Coupled equations always scare me. Everything depends on everything else. How do you ever untangle that?
With eigenvectors. By the end, you'll see they're the secret coordinate system in which the whole system falls apart into independent pieces. Here's the setup. We have a vector of quantities, and its rate of change is a matrix, A, applied to the vector itself. That single line hides any number of coupled equations.
So the matrix A is the rulebook saying how each quantity's change depends on all the others at once.
If A were diagonal, each rate depending only on its own variable, we'd be done. Each line would just be our friend from last time, growth or decay by an exponential.
But A usually isn't diagonal. The off-diagonal terms are the coupling, and that's what makes it a tangle. So the goal is to somehow get rid of the coupling?
Let's see what A actually does. Watch it act on the whole plane. It stretches, shears, rotates. A generic arrow gets sent off in a new direction entirely.
So most vectors get knocked sideways when A hits them. Their direction changes. That's the coupling made visual.
Look carefully, and you'll spot exceptions. A few special directions where A only stretches the arrow, leaving it pointing exactly the same way.
So those arrows don't get rotated at all, just scaled. Those must be the eigenvectors.
That's exactly the eigenvector equation. Along the eigenvector v, the matrix A behaves like a single number, lambda, pure stretching, no turning.
So in that one direction, the complicated matrix collapses into ordinary multiplication. That's a huge simplification.
And the eigenvalue isn't just a label. Its size sets how fast things move along that direction. A big positive lambda means rapid growth. A small negative one, a slow fade.
So the eigenvector says which way, and the eigenvalue says how fast and whether it grows or shrinks. Direction and destiny in one package.
To find these directions, you solve this. The values of lambda that make A minus lambda collapse space flat. Those are the eigenvalues, and each one comes with its eigenvector.
So it's a recipe. Get the special stretch factors first, then the directions that go with them.
Take the matrix with rows 2, 1 and 1, 2. Set the determinant of A minus lambda I to 0. That's 2 minus lambda squared minus 1 equals 0.
So 2 minus lambda is plus or minus 1, giving lambda equals 3 or 1. And the eigenvectors come out to 1, 1 and 1 minus 1.
So the system splits into an e to the 3t mode along 1, 1, and an e to the t mode along 1 minus 1. Concrete rails. Here's the payoff. Start the system on an eigenvector. Then A times x is just lambda times x. So the whole vector equation collapses to a single one. Rate equals lambda times amount.
That's last episode's law exactly. So along an eigenvector, the answer is just e to the lambda t. The coupling vanishes.
So a solution that starts on an eigenvector simply slides along that line, scaling by an exponential. It never leaves the line. The eigenvalue sets the speed of growth or decay.
So eigenvectors are like rails the system can run along without ever steering off them.
And any starting point is just a combination of eigenvectors. Because the system is linear, the full solution is the sum of those simple exponential pieces, each riding its own rail.
So we solve the easy one-dimensional problem on each rail, then just add them up. The tangle is gone.
Picture two masses joined by springs. One eigenvector has them swinging in step together. The other has them moving exactly opposite. Each pattern oscillates at a single, pure frequency.
So any messy motion of the two masses is just a blend of those two clean patterns. The eigenmodes are the building blocks of the whole dance.
This is the real meaning of diagonalizing a matrix. You rotate your viewpoint into the eigenvector coordinates, where the system is a set of independent one-dimensional problems. Solve each trivially, then rotate back.
So eigenvectors aren't an abstract exam topic. They're literally the coordinate system, where a hard problem becomes easy.
Now let's see the whole picture at once, the flow of the system in the plane. With negative eigenvalues, every trajectory drains inward to the origin, a stable equilibrium.
So no matter where you start, you slide down the rails toward the center. That's a system settling to rest.
A fair warning. Occasionally, a matrix doesn't hand you enough independent eigenvectors to cover every direction. Those defective cases need a small repair, but the spirit of the method is unchanged.
Good to know it isn't always picture perfect, but the core idea still carries the day.
Mix the signs, one eigenvalue positive, one negative, and you get a saddle. The flow rushes in along one eigendirection and is flung out along the other.
So the eigenvectors are the crossroads of the whole flow. One rail pulls you in, the other throws you out. The signs of the eigenvalues decide your fate.
So a single glance at the eigenvalues tells the story. All negative, stable, everything decays. Any positive, unstable, something blows up. Mixed, a saddle.
One set of numbers, and you know the long-term destiny of the entire system without solving anything in detail.
Here's where it ties back to E beautifully. If the eigenvalues are complex, the exponentials become rotations, and rotation, we saw, is oscillation.
So real eigenvalues give growth and decay along lines, and complex ones make the system spiral and oscillate. The same E, wearing both hats again.
And if the eigenvalues are purely imaginary, no real part at all, there's no growth or decay, only rotation. The system orbits forever in closed loops, a frictionless oscillation.
So a perfect, undamped pendulum is the imaginary eigenvalue case, circling its phase plane endlessly, never winding down.
And there it is in the flow. Complex eigenvalues with a negative real part spiral inward, a damped oscillation winding down to rest.
That's the swing coasting to a stop, the shock absorber, the RLC circuit ringing down, all written in the eigenvalues.
All of this folds into one gorgeous object, the matrix exponential. E to the a times t evolves the entire system, and computing it is exactly the act of working in eigencoordinates.
So even for a whole matrix, the answer is still an exponential, just promoted from a number to a matrix. really won't let go.
This single idea is everywhere engineers and scientists look at things changing in time.
Give me the examples. I want to see how far it reaches.
Couple two masses on springs, and the eigenvectors are the normal modes, the special patterns where everything oscillates at one clean frequency. Buildings and bridges have them too.
So engineers find a structure's eigenmodes to make sure the wind or an earthquake won't hit one and shake it apart. Eigenvalues are a safety calculation.
And it isn't only continuous time. Step a process forward again and again, and the dominant eigenvector takes over, which is exactly how the original PageRank scored the importance of web pages.
So the algorithm that organized the early web was at its heart finding a single eigenvector. Eigenthinking really is everywhere.
And it reaches past linear systems. Near any equilibrium, even a wildly nonlinear system looks linear up close, and the eigenvalues of that local matrix tell you whether the equilibrium is stable.
So you linearize near the resting point, read the eigenvalues, and you know if a small nudge dies away or grows. That's a huge shortcut.
Step back, and the whole arc connects. Last time, the exponential was the eigenfunction of the derivative. The shape differentiation only scales. Today, eigenvectors find the directions in which a system does the very same thing.
So find the directions where the operator just multiplies is the same idea in both. For one function, it gave e. For a system, it gives eigenmodes evolving as exponentials? Let me sum it up. Eigenvectors are the directions a matrix only stretches. Put a differential equation in those coordinates, and it splits into independent one-dimensional pieces, each evolving as an exponential.
Exactly. The eigenvalues then read off the destiny, decay, growth, or oscillation. Eigenvectors are simply the natural coordinate system of any linear system in motion. To go deeper into phase portraits and stability, these build the whole picture carefully. We've seen systems evolve along their natural directions. Next, we follow a wiggling charge until its field tears loose and flies away as light.
From eigenvectors to antennas. See you there.
If it finally clicked, subscribe. It really helps. And I'll see you in the next one.